Walk into any large automotive body stamping plant, and you will notice something that does not fit the mental model of a factory floor. The biggest machines in the building are not tall. They do not tower above the production line. Instead, the floor around them drops away. The press itself extends downward into a pit that may reach 10 to 15 meters below the factory floor level. The working surface of the die is at approximately ground level, with the majority of the machine's structure buried in reinforced concrete below it. The largest tandem stamping lines can weigh 3,000 to 6,000 metric tons per press station and stand 15 to 20 meters tall. Building them above ground would require a factory with ceiling heights of 30 meters and a structural steel frame capable of housing the machine's vertical extent. Instead, the industry builds them underground because of a physics problem that has no above-ground solution at this scale. That problem is vibration. The confusion around large stamping presses comes from underestimating the magnitude and character of the dynamic forces they produce. A stamping press does not apply force gradually. It applies force impulsively. The ram accelerates downward under hydraulic or mechanical drive. It contacts the sheet metal blank at high velocity, decelerates rapidly as the die closes and the metal deforms, then reverses direction. The entire press cycle on a high-speed tandem line takes approximately 3 to 6 seconds. During deceleration, the force can reach 2,500 metric tons. The reversal of that force when the press snap-through occurs produces a dynamic impulse that propagates through the foundation as a seismic-like vibration. On a large tandem line, these impulse events occur every few seconds continuously for 2 or 3 shifts per day, 7 days per week. The cumulative vibration energy transmitted to the surrounding environment is enormous. Managing it is the fundamental challenge that drives the underground installation strategy. To understand the scale of the forces involved, consider a large progressive die stamping press used for producing automotive roof panels or door outers. These components require large blanks and tight dimensional tolerances. Such a press might have a rated capacity of 2,500 metric tons. The press bed, the lower structural element that supports the die and transmits the load to the foundation, may weigh 600 metric tons by itself. The uprights are vertical columns connecting the bed to the crown. These are massive steel structures, each weighing tens of tons. The entire machine, including the drive system, may weigh up to 3,000 metric tons. Installing this requires a foundation capable of absorbing dynamic loads. Most people assume underground installation is primarily for height management, keeping the press within the factory ceiling. That is only a secondary reason. The primary reason is vibration isolation through mass and soil coupling. A stamping press foundation is not simply a slab of concrete. It is a massive concrete block, typically weighing 3 to 5 times the press itself, engineered to absorb impulse forces without transmitting disruptive vibration. The natural frequency of the foundation soil system must be well below the press's operating frequency. Burying the foundation achieves this effectively. The surrounding soil provides distributed support over the full surface area, and burial depth increases the effective mass of the vibrating system. The result is a foundation that dissipates the press impulse into the ground rather than transmitting it as a propagating wave through the factory floor. The foundation design for a large stamping press is a specialized branch of geotechnical and structural engineering. It begins with a site investigation, using soil borings to characterize the bearing capacity and damping properties of the soil. The foundation block itself is typically a reinforced concrete monolith, cast in place within a deeply excavated pit. Dimensions are calculated to place the system's natural frequency significantly below the lowest press operating frequency. For a mechanical press operating at 10 to 15 strokes per minute, the foundation soil system natural frequency must be extremely low. This requires a massive foundation and large soil contact area achievable only with a deeply buried concrete block. Between the press frame and the foundation block, spring damper isolation mounts are installed. These arrays provide a compliant interface, further attenuating the transmission of high-frequency impulse components. The isolation mount, stiffness, and damping are tuned to the press's operating frequency for maximum attenuation. The snap-through phenomenon deserves attention because it is the most vibration-producing event in the press cycle. Snap-through occurs when the stamped part is fully formed and the stored elastic energy in the frame is suddenly released. The frame springs back elastically, and the energy released is transmitted to the foundation as an impulse. On a large press, this snap-through impulse can be 2 to 3 times the magnitude of the peak forming force. This event produces the characteristic sharp bang and the highest vibration amplitudes at the foundation. Die design plays a role in managing this. Progressive designs complete features at different positions along the stroke. Releasing the blank from the die gradually can reduce the sharpness of the snap-through impulse. But the impulse cannot be eliminated entirely for deep draw stampings where the metal must be formed completely. Underground installation is used globally by major manufacturers like Toyota, Volkswagen, and General Motors. These facilities install press lines in pits with foundation depths ranging from 8 to 15 meters. Depth varies with soil conditions and the proximity to sensitive equipment like coordinate measuring machines. In urban plants, vibration barriers such as trenches may be installed around the press pit perimeter. The design of a large stamping press installation is not just a machine installation problem. It is a combined geotechnical, structural, and vibration engineering challenge that must satisfy multiple constraints simultaneously. The system has defined operational limits that interact with the foundation design. Press speed, the number of strokes per minute, determines the frequency of the vibration impulses, and therefore the relationship between the excitation frequency and the foundation soil system's natural frequency. Operating a press significantly faster than its design speed can move the excitation frequency closer to the foundation system's natural frequency, increasing vibration amplitude through resonance amplification rather than reducing it. Die wear affects the snap-through character. A worn die that does not form the part cleanly produces irregular snap-through events with higher peak impulse amplitudes. Foundation settlement over time, as the soil beneath the foundation consolidates under the long-term static load of the press, changes the foundation soil contact area, and therefore the system's dynamic properties, potentially shifting the natural frequency in ways that affect isolation performance. Periodic vibration measurement is therefore part of the maintenance at the press foundation and at sensitive points in the surrounding factory, and significant changes in vibration levels trigger engineering review of the isolation system. So why are the largest stamping presses in the world built underground? Because the impulse forces generated during each press stroke produce vibration energy that must be absorbed locally rather than transmitted as propagating waves through the factory floor. Achieving isolation demands a foundation mass several times larger than the press. A foundation soil system natural frequency well below the press operating frequency, and spring damper isolation mounts between the press frame and the foundation. All of these requirements are most efficiently satisfied by a deeply buried foundation block that couples the press's dynamic forces to a large volume of surrounding soil. The underground installation is not a concession to building height limitations. It is the engineering solution to a vibration problem that has no above-ground equivalent. Every automotive body panel on every car manufactured in a large stamping plant was produced by a machine that spends most of its existence below ground level. Not because it was hidden there, but because the physics of impulse force management demanded it. What happens when a foundation shows signs of settlement or cracking? How is the condition assessed, and what remediation options exist in an active production environment? The remediation engineering reveals how tightly dimensional performance is coupled to foundation condition and why minor civil engineering problems can have severe consequences. I covered that in another video.